Alrighty. Hello everybody. Welcome to the third sort of, I guess, chapter of our Math of Motion series. This is a live stream. We're just going to look into vectors and some of the cool math that we can do with them to learn stuff about them and solve some problem that we might come up with. And particularly we're looking at motion. So we're looking at, say you have a, I don't know, oh here we go. Let's say we have a controller and you know something about its position and you want to know something about whether or not it's going in a straight line, or if it's going in a circle, where the center of that circle would be, etc. I guess where we're at, number one was like chapter 1. Well, might as well write this out. How's it? So we got the math of motion. You could say that chapter 1 was like the real fundamentals, where we just look at sort of like it was almost just like one-dimensional adding and subtracting sort of stuff. The fundamentals. And I guess two was the live stream I did yesterday. That was like if you have vectors and you're wanting to look at their angles and just a little bit of stuff about radians and a little bit of stuff in trigonometry. So I guess it would be like the basics of vectors, vector basics maybe. And I'm gonna touch on a few things that I did yesterday that I'd like to. There's really one thing in particular I'd like to do again, and we're also going to look at, I guess, mostly what this stream will be about is if we'll come up with a few problems, and then it'll be mostly about how they're solved rather than the solution itself, if that makes sense. A lot of working with vectors will be like, oh, I'd really like to know, I don't know, like let's say tilt brush, right? If you got I'll get that controller again. You got a controller that's moving through space, and you want to know, you want to draw like a procedural mesh at a certain direction coming off whatever direction the controller is tilted at. Then you sort of got to do a bit of math to figure that out. And I guess what chapter 3 of this series will be is sort of ways of approaching that math and some of the techniques we can use. All right, so I guess I'll call that, I guess, I don't know, how to solve vector problems or something. Solving vector problems. Something like that. Okay. So let's get started. Oh, you know what? Before we do, I'll just quickly list off. I've got a little checklist of things I'd like to do. I might as well write them down. And I guess one of the first one's just really going to be, there's some notation I'm going to be using. So I'll just clear up what that notation is, what it means. So vector notation. Vector notation. The second thing I'd like to look at is we did look at signed angles, and I think like you got the angle between two vectors. We looked at one way of solving that problem. I want to look at another way of solving that problem because it's related to the next thing we're going to look at, if that makes sense. Okay, so the second thing we're going to look at is unsigned angles. Unsigned angles, angles between vectors. And I guess the next thing we're going to look at is really kind of like tied into that, and that is if you have a line and you have a point, what is that position that's closest to that point on the line? And you can figure out all kinds of stuff from that. You can say like, oh, you can learn the direction of the direction from the line to the point. You can figure out how far away that point is from the line. Let's say, what's an example? Oh, it is used a lot in like, if you in collision, you could use it for collision detection. If you had like some wall and you want to know if something was too close or far from it. And this is a subject that's it's done quite well in a series called The Nature of Code by Dan Schiffman. So I will do I'll just quickly show you the link to that when we get into it. But yeah, that's going to be really valuable as well. So, and again, that'll be something it's kind of like how to solve that problem will be really interesting. Really interesting learning the tools we use to solve that. Okay, so I'll just say a nearest point on line. That's another way of saying that would be that, you could also figure out the distance of a point to a line. Another thing would be the direction of a point to a line. Okay, so we got those two. Next one is where we're going to look at, and I did this a little bit yesterday. I wasn't really happy with how it went. I've got some notes to help me out this time. The next thing we're going to look at is what's called the slope-intercept. Slope-intercept. I guess you call it notation, maybe. Slope-intercept form of a vector. In other words, we're used to looking at a vector as an x and a y position, but that's not the only way we can look at a vector. We can also talk about where it intersects the y. I won't go too into it. We're going to look at different ways of writing a vector, and from that we're going to be able to do some cool stuff. Like, for example, if you have a line going this way and a line going this way, and you want to find out where they intersect, then we can figure that out. So next thing we'll look at is the point of intersection. Point of intersection of two lines. All right, so that's the next one, and after that, we're going to start asking ourselves some questions about circles. About if we, in some application, if we know that the user is trying to draw a circle, or we want to know when they try to draw a circle, we're gonna learn how to do that, how to figure that out. The first thing we're going to learn is if you've got a controller tracking through space and you want to learn what you want to predict what the next position of that motion would be, then we'll learn how to do that. So I guess that'll be called next point on a circle. I don't really like that. It's kind of like the predicting the next position on a circle or something like that. I'll just write next point on circle. So if someone's drawing a circle, then what's the next point they're going to draw? Alrighty. After that, we're just going to do one more thing with circles, and that's if you want to know, so you know sort of like where the next position they're going to draw. But let's say you're doing like a magic game and you want them to be drawing runes to do that magic or something like that. Maybe you want to figure out where the center of that circle they drew was. You don't want to, if they're drawing a circle, then you don't want to like create your particle effect or whatever in the like where the controller is. You kind of want it to be in the center. So we'll look at how to find the center of that circle. And yeah, obviously, like from that, we'll also know the radius of the circle and things like that. So I guess I'll call that center and radius of circle. Center and radius of circle. Okay, and there's also, I also just wanted to mention that with all of these, well except for vector notation, I've got like another agenda, and that is this, and it's sort of related because I want it to be really easy for both myself and others to not need to store this stuff in your head and to have a really like a quick reference to be able to be like, oh yeah, that's right, I did learn about slope-intercept notation in high school, and I just need a quick reference for like a refresher. So I've got this this website that I'm sort of just like putting together with some examples of some examples of these like I don't know, you call it the building blocks that we're going to use to solve these vector problems, you know. So here's one that's showing like the change in position between two vectors. Here's just showing just the magnitude of that. Oh, this is I'm like, wait, I'll fix this. It looks better when I looked at it last, just because at the moment we're looking at the live one that's on the website. I haven't updated it yet. I've got some better examples now. This one's speed, so how many, you know, pixels per second something's moving in, etc. And all the code will be accessible, so you know you can just quickly just have a look at all that. Anyway, that's that. Let's go ahead and get started with vector notation. Alrighty, vector notation. Okay, so there's just 4 things I want to look at. Let's see. So the first one, the first one is, because it's just like when we're talking about vectors, when we're writing about vectors, we want a little bit of shorthand. We don't want to write like magnitude or angle or that sort of thing. The page would fill up really quickly. So what I'll do is I'll just show you the ones that I'll be using. You know, yeah, I'll just show you the ones I'll be using. Let's say you got a vector. This is your x and your y axes, and here it is. There's your vector. First thing I want to talk about is a normalized vector, or the direction. We'll call this vector A, by the way. This will be the direction of A. So that's a little hat on top of it. Means that it's got a magnitude of 1. Okay, so if this is 1 on the x, this is 1 on the y, then something like that. Something like that. Okay, so that's what the little hat means. So hat equals direction, otherwise known as normalized. Okay. The next thing I want to look at is a magnitude. So if it's not a normalized vector, maybe you want to know how long it is. So the magnitude would be the length of the vector, and that's just got two pipes or 2 lines on a line on either side of it. Okay, so that's your magnitude, otherwise known as length. All right, and the next one I want to talk about is angle or theta. This is getting a bit messy, so what I might do, I might just draw it again over here. I don't have an eraser on this program yet. Okay, anyway, so this is the angle, and this is represented by what we call theta. I think theta is like one of those Greek letters. So that just means angle. So it's like an O with a dash through it, sort of thing. And the last one I want to look at is this one. It's a little triangle, and that just means the delta, or the change in something. Might be change in time, might be the change in between 2 vectors, might be the change in an angle. But if you see this little triangle, all it means is a delta. I think delta is the name of the Greek letter, and it also means change in math world. Okay, so that's just a bit of the notation that we'll be using. Now let's go ahead and get started with the unsigned angle between 2 vectors. And this one sort of uses the dot product of vectors. So we'll look into what the dot product is, and then we'll look at what the code is for it. Excuse me, I'll just I'll just get started. I'm just trying to think the best way to approach it. Okay, so dot product, right? Dot product, and again, wait, before I go into this, I will just quickly show you guys this this video, because I'm rehashing this video that Coding Train has done. coding train, I'll just call it, if you type in dot product, I don't know if it only does this for me, but if you type in if I type in dot product, then, oh no, okay, never mind that, never mind, oh yeah, here it is, okay, yeah, okay, so it is on the first page, a little bit down. Okay, so dot product and scalar projection. This video by Danny sort of explains it all really well. I'm just for the, I don't know, for the case of progression and what we're sort of going to be building off, I just thought I'd put it in this series as well. Yeah, and have a go at re-explaining it. But yeah, no, I definitely recommend watching this video if you want a real holistic understanding of the dot product and what he's calling scalar projection is I guess that's like that's the math term of what we're going to look at next, which is the if you have a line and you have a point and you want to know the nearest point on that line to the point you have. Anyway, so we'll get started, and we're going to first look at the dot product because it's related to what we're going to look at next. Okay, so bear with me. The dot product is simply if you have two vectors, one's called A, one's called B, then it's A dot x times B dot x plus A dot y times B dot y. Okay, so that's what the dot product is. When someone says dot product, that's what you got to do to the two vectors to find it. Now, there's an interesting thing about the dot product is you can also write it in another way. There's two ways of writing it. So saying this is the same as saying something else, which is the magnitude of A times the magnitude of B times the cosine of the angle between A and B. Okay, so it's the same thing. And the cool thing about that is if I can say, I'm just going to go ahead and write this out on one line so we know this is what we're going to do a decent amount of in this video is when you have an equation, you got to move stuff from one side to the other side of the equation to find the piece of information that you're looking for. Okay, so let's say A dot x times B dot x, make it capital A dot x times B dot x plus A dot y times B dot y is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Now, what we're going to look at first is what is the angle between them. So what we're after is this value here. We're after theta. Okay. So what we need to do is we need to start moving some stuff around, right? What are we going to move around first? Well, what we need to do is we need to get theta by itself. That's the end goal. So first of all, let's go ahead and get cosine theta by itself. Let's just do that. So if we said A times B times cosine theta, all right. So if that's this side of the equation, let's go ahead and move that magnitude of A and magnitude of B to this other side of the equation. How do we do that? Well, if we divide both sides of the equation by this amount, then that's cancelled it out on the right-hand side. Okay, so in other words, we could say A dot, I'm just going to write it in little letters so I don't run out of space, A dot x times B dot x plus A dot y times B dot y divided by the magnitude of A times the magnitude of B is equal to the cosine of theta. Okay, so now we've got cosine of theta by itself. This is something that I did look into trigonometry yesterday, and I did sort of touch on it, but I'm just going to make it a little bit clearer. When we talk about moving things from one side of the moving things from one side of the equation to the other, we sort of get that, right? So if you have I don't know, say I don't know. Oh, I don't know if I should get into it. I kind of do want to get into this because it kind of is important. I'm just gonna quickly make some notes. Sorry. So we know, like, let's say, just ignore this for now. We know that A plus B equals C. We could also say, if you wanted to move the that B to the other side of the equation, you could say A equals C minus B, right? Because you subtracted B from both sides of the equation, and that's how you got A by itself. Okay. We also know that we can do the same with multiplication and division. So A times B equals C. Well, if you divide both sides by B, then you say A equals C over B, because we've made a division there, and we've also cancelled this division out. Okay, so we sort of get the idea of moving things from one side of the equation to the other. What I'd like to look at next, just gonna do some undoing if that works. It's a very early stages drawing program. Okay, that's sort of working. Okay, what we're gonna look at next is how do we do that with a trigonometry function? And it's really nice. There's a really simple way to do it, and that's called the inverse trigonometry function. And it looks like this. So instead of okay, so we'll just do it with this example, right? If we want to move the cosine, if we want to get theta by itself, then all we need to do is take the other side of the equation and put that in the inverse cosine function, which is a little bit like, you could think of it like cancelling out cosine on this side of the equation and cancelling out cosine on this side of the equation. Kind of like in that same way. So this looks like this, right? I'm just going to use shorthand for this. This dot product is getting really messy, right? So another way of writing a dot product, I'll just write it up here, A dot B, okay? That's another way of writing the dot, like literally just a big dot. Okay, so I'm just going to keep that there so we can make this a bit neater. So the inverse of a cosine looks like this. It goes cosine minus 1, then in brackets, A dot B over magnitude of A times the magnitude of B. Okay. And that will equal theta. All right. So that's our angle between two vectors. And I guess one thing I wanted to note about the difference between this and what we were looking at before is that this is the unsigned angle. In other words, unsigned angle. So yeah, that's the angle. I'll just draw a few examples. So if you have it's easier x and y. If you have an angle A and an angle B, then it'll be this angle between them. If it's, let's see, if it's, okay, there's the angle. If it's A here and B here, then it'll be that angle between them. If you flip them around and put A here and B here, it'll still be that angle between them, and it'll be it'll always be a positive number. I guess that's what we mean by the this is the unsigned angle between. Okay. Yes, so that's the unsigned angle between. Let's quickly look at that in the code before we go on to the next stage. Kind of worth checking out. And yeah, and then we'll look at what we can do with that to find the difference between the distance between a point and a line. Okay. So here's our examples. Let's see. We've got angle between. I thought I added the. Oh, well, this is perfect. If I haven't added the angle between, then we can go ahead and do that. Okay, so what we got at the moment is the signed angle between, right? If it's negative, then you see the negative. If it's positive, you see the positive. What we're going to do next is we're going to add the unsigned angle between. I'm just going to I thought I did this yesterday. I'm just going to double check that it's not in one of the other examples. Okay, angle. Okay, yeah. Okay. Okay, so I have done it with just a regular angle of one vector, but I haven't done it with the angle between two vectors. And, I mean, you can sort of think about it in the same way. Like, this is kind of like the angle between this vector and a vector that's, I don't know, you know, just 1 on the x-axis and 0 on the y-axis. You know what I mean? Wait, I'll show you what I mean. I mean, this is really the angle between this vector and this vector. In a way, it is an angle between. But we're gonna look at if this one's here and there's another one, for example, this one. So if you've got two vectors, like one's there, one's there. Okay, so let's have a look at our angle between example. Angle between. Here we go. So this is what I've got so far, and I've sort of you can see that I'm getting this theta equals the signed angle between two vectors. We're not going to look at the signed angle. We're going to look at the unsigned angle. Okay, and I'll show you guys the math for it before we implement it. In our vector 2, this is our vector 2 class. It's just got all of our vector 2 helper functions. And yeah, this will be you guys can have a look at it if you need a reference, that sort of thing. But yeah, this is exactly what we wrote. This function here, this angle between, exactly what we wrote in the program, but now it's in code. Okay, so first of all, we've got this dot product function, which is just up here, a.x times b.x plus a.y times b.y. Okay, so I mean, I might make this a bit clearer. Why not? We're in JavaScript. We're not worried about. Sometimes you think like, oh, performance. You don't worry about that for explaining things. It's better to be clear with the code so that you know what's going on. Okay, so we'll just call it const dot product equals dot ab, and we'll also call this next one const combined magnitude, the magnitude of a times the magnitude of b, right? So const combined mag equals magnitude of a times magnitude of b. Okay. Magnitude of a times the magnitude of b. Alright, so now all we need to do, acos, math.acos, that's the inverse cosine I was talking about. And we're just going to say inverse cosine of dot product divided by combined magnitude. Okay, and now we'll just go ahead and implement that in the example. Okay, so in this example, this is if you haven't seen this before, this is a program called processing or P5, and what I've got here is I've got this these buttons. What they're doing is they're saying which update function should I use. So in the loop, which loop function should I use? So in this angle between example, this is what would happen in one frame. Okay, and we're passing in the position. This is the position of the mouse. Is pos b. P is the P5 instance. So that's our drawing object, as it were. So you can say p.line, p.set the thickness of the stroke, etc. And UI is that's the object we can use to draw this little information box over here. Anyway, let's go ahead and write in our unsigned theta function. Simply going to be like we've got this theta here. I'm going to rename this to sine theta. Signed theta, just to be clear. Theta, sine theta. And where else was it written? Oh yeah, if sine, okay. So really, we don't need to everything here, everything here, all of this code, that's just for drawing it. All that's giving us the example is the math that we just looked at. This is just for that project I was talking about, for the website. Okay, so we'll say const theta, unsigned theta equals vec2 dot angle between pos A and pos B. Okay, let's go ahead and have that printed out as well. We'll call this one unsigned. Oh, this one's signed, and this one unsigned. And that's going to be between, so going to be between 0 to pi. Okay, so it's always going to be the shortest angle between two vectors. You won't get one that's bigger than pi, which is also known as 180 degrees. Yeah, and so we'll go ahead and have this printed out. Unsigned theta. Okay, and it's our angle. Okay. So, like, you notice that they're exactly the same. Signed and unsigned are exactly the same until we go in the negative direction. Then our signed angle will not be. Our signed angle will not be negative, which means it's positive, right? Sorry, I got that mixed up. Our unsigned angle will always be positive, and our signed one will have the negative value. Anyway, yeah. So that's our unsigned angle between two vectors. Now let's have a look at the nearest point on a line. Yeah. Okay. So I'll just start. First of all, I'll just show you an example of what I'm talking about. Nearest point on a line. Okay. So let's say we have a line. Let's say we have a line. Let's say we have a line that looks like this. Okay, we have a line. And let's say we have a point. This would be our point. I'm just going to call this point A. No, I'm not gonna call. I know this sounds pedantic. I wanna just. I've got a way of thinking about these sorts of things where my A, B, and C need to be the A, B, and C. Okay, so we've got a line. Let's just say we've got a line. Any line. We've got a line looks like this, and we know it's a line because we have a point A and a point B, right? So it's when we say a line, we mean we have two vectors, and if you were to go from one vector to the other, that's the line we're talking about. Of course, it does extend imaginarily in a way. It extends forever in both directions. But that's sort of how we're defining a line. And now we can say we have a point C, which is our point. Well, we should call it a point. We should call it wait, 1 minute. Okay, I've got a little visualization aid. Okay, we have a robot. All right, this is a little robot who's at point C, and so he's done a little. You call it. This is just sort of a way of visualizing it. He's got a little depth sensor here, right? And let's say he's done a little depth sense at point A, and he said, "Oh, okay, well." There's a wall here at point A, and it's this far away. And there's a wall here at point B, and it's this far away. You know, it's something like that. It's not, it's just a way of visualizing it, right? So he's got these 2 points. He knows, let's just pretend he knows where they are in world space. And he wants to know how far away he is from that wall. Okay, so what do we need to do to figure that out? Well, this is where we're sort of starting to get into, like, how do we solve this problem? Okay, so what do we know? We know that if you have a line, you have that point, the shortest distance between them, this line here, we know that's going to be a right angle. Right, it's got to be a right angle. So that's going to be the shortest distance. Now, as soon as we have a right angle, we're able to start working stuff out. We can say, like, oh, well, if we've got a right angle, then we can start using trigonometry to solve this problem. If we know the angle here, then we're getting really close to figuring out what this point, we'll call this point D, figuring out where this point D is. And guess what? We just figured out what the angle, we just figured out how to say what's the angle between, we know how to do this, right? I'm just going to write it out. We know how to say, we'll call this angle BAC, right? So we'll say angle B, angle of BAC, right? The angle from point B to point A to point C. We'll say that angle is the angle between this vector and this vector. Sorry, I don't know if you can see that. The angle between AC and AB, you know? Angle between, which we've already written a function for, right? Angle between, almost run out of space, AC and AB. I know it looks like I've got heaps of space on the screen, but I'm using like this iPad where the space is much short. Like I'm just able to fit it in there. Okay, so that we know that angle, and once we know that angle, we're able to learn the distance between A and D. So distance between A and D. This is trigonometry. This between A and D is this. If this is the adjacent, right? I'm just going to put a little arrow here. It's the adjacent line to the angle. Distance between A and D. The adjacent is always equal to the cosine of the angle multiplied by the hypotenuse. Should I explain that? Yeah, we might as well. Okay, so we got this, so might as well. Okay, so SOHCAHTOA, right? We're going to use the ka part of the SOHCAHTOA. Cosine, this is just a formula. Cosine of theta equals the length of the adjacent over the length of the hypotenuse. Well, we know the length of the hypotenuse is the magnitude of A to C, right? Because this is our hypotenuse. And so we're able to say that our adjacent, if we rearrange that cosine formula, we could say A equals cosine theta multiplied by H, because we've multiplied both sides of the equation by H. I know I've reversed where they are, but that's sort of what we've done. Okay, and using that formula, we can say that our adjacent is equal to the cosine of theta multiplied by the magnitude of A to C. Okay, so now we know the magnitude of A to D. All we need to do is normalize this we know this A to B vector, right? So all we need to do is normalize that A to B vector and scale it up by the magnitude of A to D. So in other words, once we have this direction, which is, that direction is equal to the normalized vector of A to B, right? We can say that our position D is the normalized direction of the direction of A to B multiplied by the magnitude of A to D. So we can say D equals the direction of A to B multiplied by the magnitude of A to D. Okay, and then we've got our position D. And this magical position D is where we can work out really easily direction from D to C, the distance from D to C, etc. And so that's our distance between a point and a line. Let's go ahead and have a look at what that looks like in the code. Alright, yeah, please let me know if you have any questions or you'd like me to clarify anything or anything like that. Suggestions for other videos. Okay, So first of all, I'm gonna go to, I've done a bit of this angle between. Not angle between. I've done a bit of this nearest point on line. I'm not very happy with it because at the moment it's saying this line has to have a position of 0. Sorry, I gotta clarify. This line, it's not a real line. It's just a direction to the. Okay, so you got that red one, and it's just drawing a line from 0 to the red one. So I'm gonna change that. I'll just we'll go ahead and change it. Okay, so I'll show you guys what I mean. Maybe before I do that, I'm just gonna show you what the code looks like, and then I'll show you how to visualize it. So I'll show you what the math looks like. Okay, so let's see, where are we at? Point and line, point and line, point and point, nearest point on line, I think it's called, nearest point. Okay, cool. Okay, so this is what I'm not happy with. At the moment, nearest point on line is only taking 2 vectors, but in our example, we have 3 vectors. And 3 vectors is a far more real, it's closer to real life for what we'd actually be working with. So I don't like changing something once I've written it, because unlike C# or C++, in JavaScript, if you change like what these vectors mean, then it won't necessarily break your code. It might just give it a weird result. Whereas in C# it would say, oh, now I'm expecting 3 vectors and you've only given me 2, so won't even run your program. It's a little bit different. But what you can do is I'll just go ahead and search for every instance where this function is being used. Just make sure I don't break anything accidentally. Okay, so the only place we're really using it is in the example, and we're only using it once. That's cool. That's cool. Okay, that's perfect. So I'm giving myself permission to break my code. Vec C. Okay, so I'm just going to write a comment here that vec A and B are describing the line. Line vec C is the point. In fact, what I'm going to do is I'm going to rename these. I'm going to rename this one to line A, and this one to line B. Okay, and then from there we're going to get our vector from A to B, which will be our line, and then A to C, which will be our it'll be our hypotenuse. It'll be our hypotenuse. That'll be our A to C. This will be our A to B. Okay. So const vec AB equals sub BA, and const vec A to C is sub CA. Okay, now once we have that, I gotta please ignore all of that because I'm gonna redo it all. Okay, so now what do we need to figure out? Well, first of all, we need to hold on a second. This is just oh, I know what's happening here. Okay, this is because in this video, I did mention, I'll reiterate this. What we're doing here is also called scalar projection, and there's this video by Dan Schiffman on how to do it. And, you know, he gives a really good description of it. One of the interesting things he does is at the end of the video, near the end of the video, he comes up with, or like describes, a shorter way of writing the formula. I'm not going to use that at this point, just because the way that we've sort of got at the moment, you can sort of understand geometrically, and the other way is equation wise, as in like, oh, if we move this number to here, this number to there. So we'll just focus on the geometric one. Maybe we'll do the other one later. Okay, so that's why That's why there's like this dot product in here and etc. So ignore all this for now. And let's just work on what we were just talking about, right? Okay, so first of all, we need to get the angle between, you need to get this angle, BAC. So let's go ahead and do that. So we say const theta equals angle between vec AB and vec BAC. It won't matter what order you put those in because it'll be a positive angle no matter what. And next thing we've got to do is we got to find out using, okay, wait, we'll just refresh our memories. I need to refresh my memory. So, okay, so remember, we've figured out this angle. The next thing we need to do is we need to figure out the length of A to D, right? How far from position A is this point that we're looking for? Because we're solving for D. That's what we're after. Okay, so how do we figure that out? We got to get the cosine of our theta, multiply the length of A to C. So let's go ahead and get the magnitude of A to C and figure out the magnitude of A to D. Might just leave that there for now. Okay, so we'll say constant magnitude of A to C is equal. That's so much better having that thing to look at while I'm coding. Okay, magnitude of A to C is equal to magnitude vec AC. Okay, and we say constant magnitude of A to D is cosine of theta multiplied by magnitude A to D. Alright, and then, wait, magnitude of A to C rather. And then once we have that magnitude of A to D, we're just going to get the normalized vector of A to B. So constant, we'll call it direction of A to B equals normalize vec A to B. Alright, now we've got the direction of A to B. Multiply that by our length of A to D. So we'll say const D, pos D is equal to direction of A to B. So this would be a scale function. Scale direction of A to B by I lost it. Scale our direction of A to B by our magnitude of A to D, right? So we want to say get the direction of A to B and multiply it by the length of A to D. Magnitude of A to D. Okay, so now we've got our position D. And that's what we're solving for. So we're done. Yay. Oh, wait, no. No. Because this is a vector from A to D, but we want the position of D would be what am I saying? Okay, so what we've just solved for is this one, like in a local space, but then we want to put it back out. Let's say that A was like, yeah, if A is here, we want to make sure that it's relative to position A. So how we do that is we just say pos A D, we say this is the vector A to D. Now we just say const pos D equals add, just add them together. Add line A and vec AD. Alrighty, now let's see what that looks like when we put it in the code. Return pos D. Alrighty. Let's see. We're gonna refresh. Oh, now I'm gonna need to update the example before we get anything useful out of it. Okay. I feel like that's much smaller. Oh yeah, I zoomed out, that's why. There we go. Excuse me. Oh. Sorry. I was about to sneeze and then I didn't. Okay, so where are we at? We got this is our nearest point on line. Okay, so at the moment we're just using two positions, which I don't really like. I'm gonna say pos B because that's That's like only in local space or something. What we want to say is if the line is anywhere in world space, how do we work with that? Okay, so I'm just going to change this to by adding another position. Let's say this pos b equals x would be like I don't know, negative 10, no, negative 150, and y can be negative 50. See what that looks like. Okay, so now this isn't pos C, this is pos, we'll call this pos D. Pos D is the nearest point on line between pos A, pos B, and we're passing in pos C. So where the mouse is will be the point that, or in our example, the little robot will be our mouse. We're going to call it pos C. Okay, nearest point on line, pos A, B, and C. Okay, so to visualize that, what we're going to do is we're going to do a line between A and B. Pos line, pos A and pos B, pos A dot X and A dot Y, and B dot X and B dot Y. And then we're also going to draw a line between pos C, which will be our point that's running around, and pos D, which will be our new point. Alright. Let's go ahead and see what that looks like. What I'm just going to do is because every time I press reset, it's resetting which example we're looking at. I'm just going to change the default example to nearest point on line. Okay, so we're getting an error. B is not defined. Where's B? I might have written something wrong here. Oh yeah. Yeah, that's not right at all. Sub BA. No, sub line B. Line B, line A. And same with A to C, sub line of vex C. Well really it's not vex C, it's really a pos. I like to be explicit about what a vector is. Is it a position, a direction, or a point on a line, etc.? Okay, pos C and line A. Okay, oh yeah, and cos is part of the math function. Math.cosine. Alright, so yeah, so now we've sort of got the answer. I just like to change how it's visualized a little bit. And also we'll figure out the direction and the distance, etc. Let's see, nearest point on line. Oh yeah, so I just want to do a little ellipse for the pos C as well. Pos C. Do a little ellipse for pos C as well. Maybe we'll make it. What haven't we done yet? Cyan-ish. There we go. And last thing I want to do is I just want to print out the distance between our points in our line. So let's say distance is going to equal the magnitude vector dot magnitude of our we do need to work it. We do need to work this out. So we say const vec C to D. So from our position C direction to the position D, that will equal vec2 dot subtract position D from position C. From position D, okay, and then we just get the magnitude of that. Constant mag CD equals vec2 dot magnitude of vec CD. Okay, and then we'll just print out that mag of CD. Okay, oh yeah, I'll just remove a few decimal places to fixed. Okay, so now we're just getting, if it's right there, you're getting 0, and then you're getting sort of how far away it is. yeah, I guess that's about it. I guess that's about everything for nearest point on line. Might as well move on to the next one. What we're going to look at next is a little bit different. It's a little, because at the moment we've sort of just been thinking of vectors as positions in space, but that's not the only way to think about vectors, and we'll have a look at some other ones. So, where are we at? All right. So there's this concept. There's this. I guess they call it the form. There's this form of what we call a vector, which is called the slope and y-intercept. First of all, I'll talk about why we even care about this. Why are we looking at things in different ways? I want to give you a little example. Let's say we have a vector here, vector, and this is a line. Now we also have a vector here and a vector here, and this is also a line. Maybe we want to know where they intersect. And there might be a few different ways of doing it. The easiest way that I know of doing it is if we convert these vectors into what we call a slope and line form, slope and y-intersect form, then we're able to work out where this point is by moving some numbers around in the equation. So let's go ahead and get started with slope and y. It's called slope intercept. I'm not sure that. Wait, I'm just going to do a quick little. I always get confused the difference between a intercept and intersect. I'm not, because I don't know if there is a difference. Let's find out. Intercept, difference. Sound very similar. They do mean different things. Intersect is a two-valued qualitative property. If two paths are generated by Okay, so I think for our point, for our reference, when we don't care about the difference, this is saying that two paths can intersect, but they only intercept if they hit each other. Oh, that does make sense. Like you intercept a football player who's going for a goal or something like that. Like you stop them or something like that. Okay, that does make sense. But intersect is just like if the paths would cross. So I think we do mean. Oh, we could probably just use either. It's really probably not that big a deal. Okay, we'll call this the intersect. We'll call this the intersection. It looks like an intersection. Intersection. Okay. Although this, yeah, I don't know because yeah, this what we're about to look at is the slope y-intercept form of a vector, and let's have a look at how to work that out. First of all, we'll just so that's what we're gonna eventually work out. First of all, we're just gonna look at one line. Got a line that looks like this, and we're gonna say what are we trying to work out? Well, we've got this formula to work with, just like with trigonometry. We've got formulas. This is our slope intercept formula, which we're gonna. It's like the key to working in this form, and this formula goes like this: y equals mx plus b. Okay, where m is equal to the slope, and b is equal to the y-intercept. Okay? The y-intercept is where this line hits the y-intersection, and the slope is a ratio of what we call rise over run. In other words, if I go forward one unit, how many units do I go up? So we can see this we can sort of almost work this one out just by looking at it, right? The slope of this vector is about 0.5, which means we went forward 1 and we went up 0.5. The y-intercept is about -2. So in this example, to work out any point on this line, given an x value, we could say y equals, what is our slope? Our slope is 0.5 times x plus, or minus rather, plus -2. Minus 2. Okay, so we're already able to figure stuff out. So for example, if I plugged in, let's say we plug in 6 on the x-axis. No, I won't plug in 6 because I don't want y to equal 0. That'll be confusing. Let's plug in 2 on the x-axis. Okay, so we know x is here, but what's our y? Because we're not able to see it. All right, we'll pretend we're not able to see it. Okay, y equals 0.5 times 2 plus, or minus, I keep writing plus, 2, or plus, yeah, because it's kind of like plus -2, if that makes sense. It's -2, okay. 0.5 times 2 is 1, minus 2 is -1. And if we have a look, because this is sort of around like a, not to scale. It's not to scale, but we know our answer is around about -1. Okay, so that's our y-intercept. That's how we sort of figure out our slope-intersect form of a line. Okay. How would this look like in code? Like if we actually had two vectors. So this would be vector A. This would be vector B. Well, when we work out our slope, we really want to work out our slope using this this delta vector. This sort of want to create this vector from A to B, and then we can use the y-intercept using either. So for example, we've got our vector A, we've got our vector B. Let's go ahead and figure out the slope of these vectors. Okay, so first of all, we've got to figure out our delta AB. So the vector between A and B is equal to, B minus A. All right, vector, because these are vectors, little vector symbol on top of them. Okay, B minus A. Our slope, or in this case, we use M as that's a little symbol for slope. M is equal to rise over run. So slope equals rise over run. In this case, it's y over x. So we say M is equal to delta AB dot y over delta AB dot x. All right. So we know our slope, and now all we need to do is find out our y-intercept. So our y-intercept, which we call B. Once we know the slope, we can solve this equation using either the x value of our A vector or the x value of our B vector. Okay, so first of all, we've got to move the equation around, right? So if we know that y is mx plus b, we could also say b equals, because we got to, okay, I'll write this out. Let's write this out. I like to be explicit. Okay, so we know that, for our y-intercept, I'd like to be really clear here. So y, because this confuses me a lot, moving things around in equations. It's like, how did that thing on the left side get to the right side? Right, so y equals mx plus b. Okay, another way of writing that is if we subtract mx from both sides of the equation, we could say y minus mx equals b, right? So we've taken mx away from both sides of the equation. Okay. Once we know the equation to find b, we can say b equals B, yeah, B is equal to, because we know the x and the y vector of x and y component of both of these vectors, and we could use either. Let's just use the first one. So we could say B is equal to A, as in vector A dot y minus M times vector A dot X. Hi Ross, the music and guitar teacher. Played some guitar before I did this stream. Okay, so we got this vector. We got the vector A. So now we've solved our B. And so now what we've done is we've converted these two positions of A and B into what we call a slope and intercept form. Okay, because we've worked out B here and we've worked out M here. Okay, so now we can, as we showed in that previous example, we can plug in M and we can plug in the X value and solve for Y of any point on this line. Alrighty. Now that we have that, let's see what this looks like in code. Okay, I'm not sure if I already have an example of this. It might be worth writing one out because it's kind of really nice. Oh yeah, slope intercept. I do have an example. Okay, lovely. Okay, so here's our example where we say our slope, for every time I go forward 1, I go up 0, right? That makes sense. If this was a diagonal, for every time I go forward 1, I go up 1. That's our slope, right? Or if it's this way, it'd be the same thing. Now a y-intercept is a little bit interesting. A y-intercept is the position on the y-axis. I'm glad you're enjoying the videos, Ross. Which ones are you sort of looking into? Anyway, so our y-intercept is where it crosses the y-axis. So if it's negative down here and it's positive up above that x line. Okay, so that's our slope intercept. I'm just going to show you what the math looks like and what this example is sort of doing. And that's going to be in our vector class. Okay, so if I go ahead and look up, slope intersect. Okay, so here we've got our vector A being passed in and our vector B being passed in. First of all, we've got to get the vector from A to B. It's kind of like the delta one. And then we've got to get our slope, which is up here, simply the y over the x component. And then we've got to get our y-intercept, which is the as we're showing in this example. This is sort of like this notation is a little bit of how we come up with this formula. We know that y is mx plus b, and then we say y is slope is another way of saying m. And anyway, then we rearrange that and sort of solve for that. Oh yeah, Matt. No, I was really enjoying the AR Core tutorials. I was sort of hoping, like, if at some point to get back into it and make some other stuff with it. But yeah, we'll see how we go in the future. I know that this new AR Foundation series of what do you call it? AR Foundation package that Unity's working on. They're going to be creating some a remote, which will make it really easy for us to maybe do some more AR Core stuff. Okay, so now that we know our slope and our y-intercept, we can go ahead and pass that back as the Cartesian, which would mean Cartesian just being points in space, to our slope intersect form. I know it says slope intersect. Intercept, I don't know. Make up your own mind. Okay, and now the next thing we're going to look at is point of intersection. So if we have two lines, where do they cross each other? And that's going to give us, that's going to open up a world of other exciting possibilities. Okie dokie. So let's go ahead and look at how to solve that one. Okay, so I'm just going to open up our sync pane. Okay, I've lost the chat. Okay, so we've got our line A, line B. I'm just thinking of the easiest way to explain this. Okay, so let's just pretend that we've got two lines, right? Got a line here and a line here, and we know the slope and the intercept of each of them, you know. So now we can sort of work out where this point is. We sort of got to first ask ourselves, like, what do we know? What can we lock in? Well, let's have a look at this. Let's see. This is sort of where it gets a little bit. There's a big equation that we sort of got to look at. It's not big. It just needs. I want to make sure I explain this right. Okay. This is a really nice way of explaining it. So we've got this point. I'm going to call this line A and this line B. This is the line. And this is a point C. I'm just going to call this point C. Okay, so what do we know about this point? Well, we know that the C dot y, we could say C dot y equals A dot, because this point is on this first line, is on this line A, is equal to A dot M times C dot x, right, plus A dot B. In other words, we know that this point is on our line A, okay? And because we know that this equation is true. We know that whenever the C's y, we take the C's y, and it will know that it's gonna work out in that equation that we looked at, right? Because we use that equation to solve any point on the line. Now the interesting thing is, because we know that we're talking about a point of intersection where it's also on our line B, we could also say this. We could also say C dot y equals B dot M times C dot x plus B dot B. I'm using those M and those B variables that we were working with before. Okay, so once we have those two, we can also write this, because we know that C dot y solves in this equation and C dot y solves in this equation. We can say something like this. We can say A dot M times C dot x. You've got to bear with me here. A dot M times C dot x plus A dot B is equal to B dot M times C dot x plus B dot B. In other words, we know that these two equations up here, they are equal to each other. What that means is, if we rearrange them, we can solve for C dot x. Now let's have a look at how we can do that. Okay, so we know that AM times C. I'm not even gonna. Like, just saying it again confuses. So what I'll do is I'll work this out. Let's say we want to get this C dot x on its own. Okay, so we can say well, if we move this a dot b to the other side of the equation, let's go ahead and do that. Okay, so we could say a dot m times c dot x equals b dot m times c dot x plus b dot b minus a dot b, right? So now we've gone ahead and subtracted a dot b from both sides of the equation. Okay, and now I know I'm going to run out of space here, but we'll see how we go. Now let's move this part of the equation to the other side. Okay. So because this being added to okay, you could say something. This is how I sort of visualize it, right? You could say you're adding b dot m multiplied by c dot x to this other side of the equation. Sorry, other side of the that b dot minus a dot b. What we can do here is we can say a dot m times c dot x, right? A dot m times c dot x I hope I'm getting this right, minus b dot m times c dot x is equal to b dot b minus a dot b minus a dot b. Okay, so we're getting closer, right? Now we're sort of getting this magical c dot x, we're sort of getting it by itself. Next step is, because we have these what we call like terms, right? As in this a dot m times c dot x subtracted from the b dot m times c dot x, because that c dot x is the same in both sides of that, both of those operations. What we can say is we can say a dot m minus b dot m minus b dot m, and I'm running out of space, but I hope this is sort of working. Minus b dot m times c is equal to b dot b minus a dot b. I know it's a fair few operations, but we're getting closer. We're getting closer. Now we have this c by itself. So all we need to do is if we divide both sides of this equation by this part, then we'll have the answer. So at the bottom here, I'm going to write the final formula. Let's see. We say c equals b dot b minus a dot b over a dot m minus b dot m. Okay, just going to double check that I got that right. I think that's right. Let's have a look in the code. I hope I got that right. There's a fair few operations in there. We'll see if it works out. Okay. So that's the plan. Oh yeah. Okay. Oh yeah. So that's most of the plan, right? Now we've solved c dot x. That's c dot x. Now to solve c dot y is really easy. We do the same way as we do it with solving the y-intercept of any equation. Or no, it's not quite the same. Okay, so I will explain this quickly. So c dot y is, we can use either of these formulas up the top here. So either this one or this one will give us c dot y, right? But now we've got our x value. It's much easier. We can just say c dot y equals let's say a dot m times c dot x plus a dot b. So you know what I'm saying? Because we know what c dot x is, we can just solve for y. And then we got our position. We got our position C. Alrighty. So let's have a look at what this looks like in the code. Where are we at? point of intersection. That's what I'm sort of looking for. I don't think I've even got an example for this. I don't think I've got an example for this. That's cool. That's cool. That means we can write an example. Okay. Let's write an example. I think I've got the math, but I haven't got the visualization of the math. So what I'll do is first of all I'll show you the math. Yeah, okay, cool. I did, yeah. Okay, I was just double checking that through all that, it was all the same as what I worked out earlier, and it is. So so we're on the right track. We've got it all right. So you can see how, I've sort of written in the notes how we've sort of worked it out. We know that this is true, as in we know that both of the slope-intercept equations work out to each other. First of all, there's a little conversion between, Cartesian positions. This vec 1a, 1b, 2a, 2b, we convert them to slope intercepts, and then using those, we find this intersection. Okay, and so we know that the equations, when we're solving for x, will work out to each other. Then we move stuff around, solve for x using that final equation we just worked out, and then using the famous y equals mx plus b, we can just solve for y as well. So let's go ahead and draw this. See what this looks like in the code. If we're able to actually see it. So what I'll do is I'll copy one of my last examples and sort of tweak it. Let's see. What's an example that's similar? Just to save a bit of boilerplate coding. Let's see. I might just click through them, see the one that looks the most similar. In fact, I think this one is slope intercept is probably the most similar in a way. Okay, we'll use the slope intercept example. So first of all, what I've got to do is I've got to create the UI button for our new example. This will be called point of intersection. Point of intersection. State is point of intersection. I'm just setting it as the default now, so that when I open up the page or hot reload the page, it'll stay on our point intersection example. Intersection. All right, and now I'm just going to add our add the file itself and add it to our index. Oh, I do have an example. Why isn't there there's no button for it? Sorry, I'm sort of ping-ponging a bit here, but you know what I mean? Like, if I've got an example, then how come I can't find it on here? I'm just gonna go ahead and find out if maybe I created the example and just didn't make it clickable. Okay, I'll go ahead and add it. Okay, I think that's what happened. It's point of intersection. So if you're just tuning in, then what I'm doing here is I'm going through some vector math, I guess, techniques for solving vector problems, and we're also building these examples on the Pirates Just Are website, so that if anyone, myself included, needs a refresher, you can really easily just access the answers on the website. So I'll just quickly show you. We've got a Pirates Just Are. It's a very new website. We've got a projects, vectors, and we've got all these examples here. So hopefully, when you're making a game, or you're doing some VR thing, there's probably enough things to worry about aside from the hardcore math. So what we're trying to do is just lock in all this math so that we know it, we have the references, we can quickly implement it from one point of reference, and that's going to make things much easier to do cool things with it when we're working with when we're making a game. Okay, so this is the idea. That's what we're sort of working towards. I'm just going to go ahead and make it so that we can view this point of intersection example. Excuse me, I had a bit of a sneeze. Okay, all I'm doing here is adding this point of intersection example. It's funny, apparently I've written it, but I haven't oh, okay, so I think I remember what happened. This is what I was doing yesterday, because yesterday I was doing a live stream. I was starting off with the basics, and then stuff was getting more and more difficult. And then I got to this point, and I was like, oh, I did not have the brains to sort of solve it, but I do now. We can do it now. So that's why I've sort of half got that example there. So let's go ahead and do it. Let's go ahead and finish it up. Okay, so this is, at the moment it's giving us our slope and our y-intercept, which is not what we want. What we want is we want to pos A and B and C, which will be our fixed values. I'll show you what I mean by that. Just gonna undo all that. So we've got our A, position A is, I don't know, 100x, 150y. Position B will be negative 100 on the x and maybe 50 on the y. And let's draw a line from A to B. Okay. Oh yeah, right. Okay, and this will be pos D. Okay, so we've got a line. This is our first line. Now let's go ahead and create our second line, which will be from pos C, which will be fixed as well. I don't know, maybe negative 150 on the y and 150 on the x. And we'll do a line from pos C to pos D. Okay. So we've got our two lines. That's cool. Now, let's go ahead and find out where they intersect. Now, we already know the math. All we're wanting to do here is really just visualize it. So we say const pos, we'll call it pos E equals vec2 dot Cartesian point of intersection, vector point of intersection. I don't really like that name. I'd rather call it Cartesian point of intersection, as in you're passing in Cartesian coordinates to get an intersection of the four of them. So I will change that. I'm just going to find out. Let's see if I could, this is how I sort of work in JavaScript. In C Sharp I could change things without worrying about it, but in JavaScript I might accidentally change something where it's working in another example. So I just do a search over all my files and find vector point of intersection. So everywhere it is being used, I'll just change it. So I'll call it, instead of vector point of intersection, so it's only in the one file, which is good. Vector point of intersection, and we're gonna find all of those and replace them with Cartesian point of intersection. Okay, now we've got that Cartesian point of intersection. The other thing I want to do is I want to rename slope intercept point of intersection. Oh no, I do like that name. Because it is explicit. Because you've got the two forms. You've got your Cartesian, which is x, y coordinates, and your slope intercept form of describing a line. Okay, so now we've got that name sort of cleared up. Try this. Pos E equals vec2 dot Cartesian point of intersection. Pass in pos A, pos B, pos C, and pos D. And hopefully, if we got all this right, do an ellipse at pos E. Hopefully that'll come up at the point where those two lines would intersect each other, or would if they'd continued on that path. Would have, okay. And would you look at that? Isn't that lovely? We've got a little a line where no matter where I point this, it's gonna find the point where those two lines intersect. Might as well. Oh yeah, no, that's all right. Visualizing like that. I think this is the reason why this is nice. Is it's showing what it's doing, even though technically we're talking about a line which would extend forever. What this is showing us is that it's really 4 points in space, and they could be as near or far away from each other, and it'll still find that point of intersect. So I don't mind how that looks. I might just it feels weird there not being any information printed out, so I might just do the pos E position. Might as well print it out. Position. We say x colon pos E dot x dot to fixed, and we'll do the same for the y. Okay, so now we're just getting a bit of info printed out. That's looking good. I hope you guys could see that. I want to sort of like balance. If I have this all the way over here, then you can't see much. But if it's all the way over here, I'm standing in the way of it. Anyway, that's the intersection of two lines. Awesome. That's how that works. And now we've got an example for it. That's really nice. I'm gonna have a little breather. I might just do like maybe, I don't much, just like 3 minutes or something. 3-minute break. Oh, I just need to have a cup of tea. Oh man, that's a good stretch. Okay. Anyway, I feel weird stretching on camera. Anyway, I'm just gonna make some tea. We'll pour some tea from a kettle and think about what we're doing next. Alrighty. Awesome, Ross. See you later. So, we're about to get, I guess, we're about to get into what I'd call like real problem-solving mode, as in, I don't know, you're a developer. Your boss comes up to you and says, hey, I got this problem, I'm wondering, is it possible for us to solve it, or something like that. And we're going to look at the type of problem we're going to solve is this problem of circles. And I guess the interesting part of it is how we sort of get to the answer. How do we get to the answer? Okay, so what are we talking about? What do I mean by circle? I mean, you have a controller. It's got a position in space, and I don't know. If you're moving it left to right, you can say it's moving in a straight line. Okay, you're moving it, I don't know, at some angle as it goes. We can work out the delta angle. But what about if in some example, let's say I always somehow visualize this as being a really fun magic game where if you're able to draw your shapes and they sort of like, I don't know, something like that. What do we need to work out? Well, one thing that would be really nice is if we knew that someone was drawing a circle. I mean, another example would be therapy. Like if you were doing an app where you want someone to, I don't know, move their arm in a really nice sort of like circular pattern like that, or or make big circles and then bigger circles, this sort of thing. Then you might want to know where that position of the circle they're making is, a really nice thing about that would be like, you could say, instead of saying like, I just think of an example like, let's say you want to use it to draw a circle. Well, you could get him to say, hey, draw a circle around this point. I want you to draw a circle around here. Are you doing it around here? Because if you're not, I won't know what you mean. If you're drawing a circle here, then I don't know what you mean. It's got to be around here. Well, you know, you could do it that way, but a really nice way to do it, if we could, is say, like, draw a circle. I want it to be at least this big, but I don't care where you draw it. That'd be a really nice way of, like, talking to a user. So what we need to do to start, like, let's say you wanted to have some sort of UI or, I don't know, particle effects or something in the center of that circle. We sort of got to start, like, start solving some problems with the circles. Okay, so the first thing I'd like to look at is if we are wanting to understand if someone's drawing a circle, we're wanting to understand where the next point on that circle is, almost like a angular trajectory. How do we work that out? Yeah, so let's go ahead and have a look at how we could do that. Okay, so we're tracking something through space, right? And, well, no, okay, first of all, let's work backwards. So let's say that we've got a circle here. Okay, this is a potential circle that someone's tracking through. Okay, and we've got their last known position. Well, it's got to be on that circle. So we'll call that pos C. We got their second last position. We know that's going to be also on the circle. We'll call this pos B. Now, this third last position, where they were, we know that the angle, there has to be some angle where it would intersect the circle, but it's not necessarily on that point. I'll show you what I mean. Let's say we've got pos A here, right? So these are 3 points that we've sort of that have come in, and we're able to that we sort of like that we're tracking from a controller or something like that. And now we want to work out. Let's say we'll call this ABC. We want to work out this pos. This would be D, right? We want to work out the next position on that circle where they're sort of moving through. Well, we know pos A doesn't need to be on that circle. In fact, it almost certainly won't be. But there will be a point. This point here, where it would be on that circle. So this is just a way of visualizing it. There's some really interesting things. Oh, I don't know if they're interesting. I find them quite interesting about what we're drawing here, and I'll just show you that in a minute. It is kind of interesting. Okay, so we got these lines, right? Because this circle is kind of like, it's made as a result of the angle between A, B, and C, this angle here, then we know that this position here, I kind of want to call this, position D now. No, I'll call this position E. Okay, this position E, we could say something like this. We could say that the direction from B to the magnitude of B to E, the magnitude of our vector from B to E is equal to the magnitude of our vector of B to C. Okay, so these are the same. Have got the same length, which is interesting. It is interesting if we're solving. Oh wait. Oh, I just realized I'm skipping ahead. I'm solving the center of the circle problem, not the next point on the circle problem. I'd like to do the next point first. I'm sorry, guys. I'm confusing us here. It's similar, but it's not the same. Okay. Okay, sorry guys. I'm just gonna bear with me here. I'll just try refresh, try again. Okay. So, we've got our circle here. We've got our pos B, our pos C, and our pos A, which might be like something like this. And we're solving for pos D, right? We're solving for this next point on the circle. Well, how are we going to work that out? Let's work out what we know, okay? we know that this next point on the circle is going to have the same length as the length of pos b to c. So in other words, the magnitude of c to d is equal to the magnitude of b to c. Once we know that, we can say, okay, well, we're getting there. We're on our way. What else do we know? Well, we also know that the angle of, let's say, I'm just drawing an imaginary line here. We know that the angle of ABC, so we say angle of ABC is equal to the angle of BCD. Okay? So we know those angles are the same. Okay, so that's what we know for sure. Now this is getting interesting because it's like, okay, so we've got those worked out. What can we sort of how else could we visualize this? What if I were to do this? What if I were to draw a line from B to C, continue on, create a new point, call it E, and make it at right angles there, okay? So as in make the line perpendicular to the line of, perpendicular to B to C, and we'll call it E to D, right? Well, the lovely thing about working with right angles is then all we need to solve our problem is trigonometry. In other words, I'm wondering if this is just going to get messy. Because we know this angle, we know this angle. We know this angle of AB to C. Just thinking of the best way to explain it. Okay, what do we know? Okay, so first of all, let's work out this angle here, because this angle is equal to this angle, right? First of all, let's work that out. So we could call this theta. Let's just call it theta. Theta equals the angle between let's say angle of A to B, angle of A to B and B to C, right? So if that's our A to B and that's our B to C, sort of in that direction, then it'll be the angle between those two, right? Angle between this one and this one. Okay, so once we know that theta, and we know that we can work out our magnitude of C to D, which is this line here, magnitude of C to D. Then we can use trigonometry. I kind of want to rotate this and just look at this triangle by itself to solve it. So what I'll do is I'll draw another triangle here, and we'll go ahead and just fill it in. So that's at point E. You know what I'm doing here? I'm just sort of just like rotating it like this. Point D here, and point C here. Yeah, point D up here. Okay, so we know our angle and we know our hypotenuse. Well, we can solve the C to E. Let's see, we'll just write this out. C to E. The magnitude of C to E is equal to the cosine of theta times the hypotenuse, right? Just like how I would work out any adjacent side of a triangle. And then the magnitude of C to D is equal to the sine of theta times the hypotenuse. Just like we'd work out any opposite side of a triangle. Okay, so now that we've worked those out, we know the C to E, and we know E to... Did I say C to D? Oh. It's E to D, rather. I've written C to D, but it's magnitude of E to D. That's what I was after. Whoops. Sorry. I've made that a bit confusing here. Magnitude of E to D. Okay. Okay, you know what I mean? So we're describing, for the sign, we're describing that opposite one. Okay. Now that we have those two magnitudes, we can work out the position of E and then the position of D. So we know that position of E, we can say pos E. Pos E, let's do a line here. Pos E is equal to position C, right? Is equal to this position here, plus the direction of beta C multiplied by the magnitude of C to E. C to E magnitude. Okay, you know what I mean? So we say we take this position C, and then we take the direction of beta C, and then we multiply it by the magnitude of C to E. Is how we get that position E. And then we know our direction E to D is perpendicular to our direction of beta C. So we can say pos D equals the let's say pos E, because we're going to go from this position E, right? Pos E multiplied pos E plus the direction of E to D, which is the perpendicular of beta C, plus the perpendicular of beta C, perpendicular of a normalized value of beta, because it's a direction vector of beta C, multiplied by, hoping you still like this is sort of like I find this, I got to refresh my mind a lot to sort of keep a handle on how this sort of works. So hoping this is sort of making sense. Okay, so then we say perpendicular of beta C multiplied by the magnitude of E to D. Multiplied by the magnitude of E to D. Okay. And that is how we get our next point on a circle. What I'm going to do next is I'll just show what this looks like in the code. Okay, where are we at? So first of all, I'll just show you the this one isn't, I don't know if this should be moving, but yeah, this is what it's sort of trying to work out, right? As your mouse is moving through the world, you're able to figure out what that next point on the circle is. Now, where things can get really interesting is if we were to keep doing that, like recursively finding the next point, the next point, the next point. Well, then we can get some sort of like work out a circle, which would be quite nice. Out of interest, one thing I do want to show you is because these delta positions are really short, then it's a really nice circle. But if I slow time down a bit, let's see, we'll go next point in circle 2. Let's slow down time. Set the frame rate to 3, right? And then I'll just go next point in circle 2. Okay, it's not going to work because it's doing this lerping thing. Okay, never mind that. It's not going to work. We'll just have to wait till the center of the circle because this one's, might work. Hold on a sec. Just bear with me here. I'd like to show you something. It's really, I find it really interesting because you can get these really nice. Oh no, it's not gonna work. I don't think. No, it's not gonna work. Okay, I'll leave it. Sorry, I'm digressing here. Never mind that. Never mind that. We'll get onto the cool shapes when we look at the center of the circle. Okay, because I guess I'll explain what's happening here. What I'm sort of doing is, instead of, if I didn't lerp, I'll see if I can show what happens if I don't, like, you know, lerping, like linear interpolation, as in instead of using the mouse's actual values, you kind of want to soften the mouse positions a bit, because it's really difficult to draw a perfect circle all the time. I'll see if I could show you what that looks like if I were to try to do that. Last sine theta. Okay, I think it's this one here. By 1. Try it. Okay, yeah. So this is what it sort of looks like if you don't lerp it. It's just like really hectic. It's sort of like, yeah, a little bit confusing. I think I might have, that might be the solution I was looking for. Yeah. So now, if I just go 32, see if this works. Oh, not really. What I'm trying to do is sometimes you can get it to create like a little geometric shape. It's sort of doing it a little bit. Yeah, it does it a little bit. You make like really interesting sort of like I don't know, you call them line patterns by doing it. Anywho, that's kind of like a, I don't know, maybe for art class, whereas for working stuff out and like, I don't know if we want to track motion or something like that, we're going to need to use linear interpolation. So we're going to want to say, don't take where the thing literally is. I want you to like take it. It's like saying take it with a grain of salt, or like, no, it isn't. It's like saying smooth the motion of the mouse. That's what it's saying. Okay, so that's how we sort of get that. We're able to sort of see a nice circle. See, I'm drawing in a circle, and we're getting more or less the center of it. We draw a big one, we get big ones. Or I draw a little one, we get little ones. Yeah, so that's things we can do with next point in a circle. This is it sort of broken down a bit. Let's have a look at what the math looks like. Next point on a circle. Okay. So this is the math for it. I don't really like how it's written. It's kind of a bit confusing. I'm not sure exactly how much cleaner I can get it though. It's essentially what we were doing, but in code form. Maybe I should. Maybe I think I'll have a go. I'll have a go at doing a line by line. No promises. We'll see how we go. Okay, we'll see how this goes. What I'll do, put that up there. Put this across here. So this is how we're sort of working out, right? We've got this I can't do in between. Okay, that's all right. Okay, so what we're sort of working out is we're working out this position. We're solving for position D. And there's a few steps we need to go through to work that out. And what are those steps? Well, first of all, we get the angle. Angle between A to B and B to C. Okay, so to do that, we need to figure out our delta AB and our delta BC. Then we get the angle between them. And all this is doing is this is saying, guess what? This angle here is the same as this angle here. Well, yeah, okay. This is where it's a little bit weird, because it's really, because it's the angle between A to B and B to C, it's really this angle here. is equal to this angle here. I'm hoping that makes sense. Okay, so once we have that angle, we also need to get the magnitude of beta c, because the magnitude of beta c is equal to the magnitude of c to d, which will be our hypotenuse in the triangle we'll be working with. Okay, and then once we have that, we can look at a direction of beta c. I'm going to move that down because we don't need that until later. Okay, because in the I'll say the next step would be magnitude of c to e would be well, that's the adjacent in this triangle we're working with, and so we can solve for the adjacent by doing the cosine of theta times the hypotenuse. Okay, and then our magnitude of e to d, out of interest, all this means by sign magnitude is it could be going this way or that way. So it means that if you're drawing a circle in the other direction, it'll also work. Our magnitude of e to d, this e to d, is equal to the opposite of the triangle that we've created. And once we have those two, we're able to get able to solve for our position E and our position D. Okay, so our position E is the position C plus the direction of beta C times the magnitude of C to E. Okay, because we know the direction of beta C is the same as the direction of beta E. It's on the same line. And we know that we just take the position of C and add the direction multiplied by the magnitude. Okay, so once we have that, so that's essentially what's happening here. And we know our A to D, our direction of A to D is perpendicular to our direction of beta C. I think I've made a mistake here. This isn't right. It's not a sine magnitude. Because the sine of... Oh, no, it is. No, it's not. It's not a sine magnitude because... Oh, no, it is a sine magnitude. I'm sorry, guys. I think it is. I think it is a sine magnitude. I'm just overthinking things. Okay. So now we've got our we can take, now we've got our position E. Our position D is E plus the direction of E to D, which is perpendicular to B to C, all right? Because that's the right angle. We take that direction and multiply it by the magnitude of E to D. And that's how we get our position D. And we can do with that all kinds of things, like drawing circles. Yeah. Anyway, that's the next point on a circle. And I guess like you might not necessarily use that case in particular, but it's a nice way to sort of start thinking about things in this way. Thinking about things in like as in thinking about how to solve these problems. How to solve these geometric problems. Okie dokie. Now that we have that, finally, we're going to look at the center and radius of a circle. It's not crazily different. It's a little bit different. All right. So, center and radius. We're also going to use that stuff we were working on before, which is the point of intersection of two lines. Okay, so this one in a way is kind of similar. It's like you know, you got a geometric problem, you got to solve it. How we solve it is quite different. Let's have a look at how we solve it. Okay, so we've got a circle, looks like this. Or maybe I'll do a nice big circle. Nice big circle. And let's say we have our where the position of something is. We'll call that pos C. And then where it was in the last frame, we'll call that pos B. And where it was in the frame before, let's say it was something like, I don't know. What if it was here? Pos A. Okay, so we'll notice that pos A isn't on the circle, and it rarely will be. That's okay, because what we can do is we can imagine this other position, this imaginary position. And I like to use the same words that I use. Yeah, okay. So I'm just gonna call this like I don't know, A2, something like that. I just don't want to. Yeah, I want to get the same letters as I use in the code. Hopefully that'll make things a bit clearer. Okay. I think I do call it pos D. I do call it pos D. I think. Yeah. So I think that we will call that pos D, and that's like where A actually would be on the circle. Okay. Now here's some interesting things I can tell you about these positions. Okay, I can tell you that because this circle is based off the angle between A, B, and C, I can tell you that the length of B to C, magnitude of B to C, is equal to the magnitude of C to magnitude of D to B. Okay, so we know those magnitudes are the same. Another interesting thing I can tell you is that the right angle of this line meets the far point. I know this isn't really drawn to scale. The right angle of this line meets the far point of this vector of this circle. Okay. So there's a right angle, and gosh, I really want to draw this to scale. It looks ridiculous if I don't draw this. If I don't draw this right, it just looks so silly. I'm drawing another one. It's really hard to draw a nice circle. Okay, that's a bit better. Okay, so we got our pos B, we got our pos C. Let's say this time our pos A will be down here. It's not too important. Pos A will be down here, and where this pos A intersects the circle, call that pos D. Okay, so what do we know? We know that these are the same. Pos B to C is the same as pos B to C. B to C is equal to D to B. Okay. We know they're the same. And what else do we know? We know that a right angle of D to B is going to intersect at this far point of the circle, which we'll call pos E. All right. And we know that this vector here, pos B to direction B to E, is the average. Oops. B to E is the average of these other two directions. So B to E. So direction of B to E. Let's see. Direction. That's not direction. Direction of B to E is the average. Is average of. That's right, average of the direction of C to E and D to E. Okay, of the average of the direction C to E, average of the direction of C to E and D to E. Okay. The direction naturally will normalize as well. Okay, because we know that, because we know that, we can do this. We can create another point. I'm going to call it F. Okay, because our point of intersection formula works with Cartesian positions, and we don't know this position E yet. This is what we're going to solve for, this position E. We don't know where it is yet. All we know is we have a direction. We have a direction going this way. We have a direction going this way, and we found a direction going this way. And we know that all those three lines intersect at position E. What we can say is position F equals B plus the direction of beta E. So we say F equals B, that's a vector, B plus the direction of beta E. Okay, and we know that we'll create another one, we'll call it G. We'll say G is equal to C plus the direction of C to E. C plus C to E. Okie dokie. So now we've got these two vectors. What's essentially two lines, and we can use our point of intersection formula to come up with this position E. So we can just say E equals, once we have those two lines, right? E equals intersection. I'm gonna write this up the top there. I'll write this up here. I would say E equals the intersect of B. Okay, this line B and F. That's our line 1, and our other line is C and G. And we're getting really close, because once we have E, and we know our direction of B to F, we can work out what we'll call H, which is the center of our circle. H is just halfway between B and E. So H equals B plus the direction of B to E, right? Multiplied by the magnitude of B to E, which you would also think of as the radius, right? Magnitude of B to E. If that's B and that's E, then the magnitude is just all the way across the radius. It's okay, plus the magnitude times the magnitude of B to E divided by 2. And there's our center. Once we have H, we can just return like if this is a code example, we just return an object where the center is equal to H, and our radius equals the direction of B to E over 2, or the magnitude of B to E over 2, or the magnitude of B to H. Take your pick. So the radius could also be magnitude of B to H. Okay. So I just completely don't like scribble. Hold on a sec. I'll just undo that scribble I just did. I've got this new undo function, but it sort of works. I've got to hit two fingers on the touchpad at the same time, exactly the same time. Otherwise, it undoes like a touch. Anyway, radius equals the magnitude of B to H. Okay. So let's go ahead and see how we can implement this. I'm going to put this over to the side because we'll be looking at it. And first of all, we'll look at the code, so it's all fresh in our memories. Okay, so I'm calling this function circle info because it gets the center and the radius of the circle, the two things you might want to know about. Okay, so you notice we've got our passing in our 3 positions. And we also got this max valid radius. This is because if you're working with, like say 3 vectors that are all equal to each other or something like that, or like some ridiculous numbers, you're gonna get like a vector that's just massive, and it won't make sense, and it'll throw all of your calculations, and sometimes it'll return it. So we've got to understand that sometimes it won't work. Sometimes, say if you're going in exactly a straight line, then there's going to be no point of intersection. We're going to get invalid slopes and this sort of thing. So we've got to be ready for that. We've got to be ready for this function to return just undefined or no object. Okay, so what are we doing? Let's work this out. Let's step through it. Okay, so first of all, direction of A to B. Well, what's A to B? A to B, we've got our position A, got our position B. We need to get the direction of A to B. That's a start. Okay, now we get our direction B to C. It's just a normalized direction. In fact, pretty sure I've got a direction function. So can't I just say equals direction? Yeah. A pos B. That's cleaner. Direction, instead of normalizing one subtracted from the other, which is essentially what direction does, but it's nice for these more complicated algorithms to be as simple as possible, so we can focus on what they're doing. Okay, direction C to B. Direction of B to C rather. Direction of pos B and pos C. Okay. Now we're working out our direction of D to E, which is this one here, and our direction of C to E. Okay, that's just the perpendicular of A to B and B to C. Yeah, I'll leave that for now. Yeah. Okay. Yeah. I'll leave it. There's something else I want to explain, but I'll leave it for now. I was just confused. Okay. Now the slope of direction D to E. Okay, I think what's happening here is we want to make sure that once we have these 2 vectors, we want to make sure that they're not parallel and they're not 0. Otherwise, we're going to get errors. Because you can't get the y intersect being because if it's a vector that's going absolutely directly up, then it's going to be if the x component is 0, it's going to try and say y over x, which is anything out of 0 is not a number. So we've got to make sure that they're valid numbers. Otherwise, we'll return nothing. So this means are they both parallel, or is one of them directly straight up? If they are, then we're going to have to throw them out. But it's so rare when you're talking about floating point values. Just worth thinking about. And then after that, we need to get the direction of B to E. Okay, so the direction of B to E is simply the average of these 2 vectors. We know that because we know that their lengths are the same. We know that the length of B to D is the same as the length of B to C, which means, yeah, it essentially means that B to E is exactly halfway between these other 2 vectors. Simply normalize the average to get that. And position F is, we're just creating this position as something to pass in. We're just describing our line to our point of intersection function. We're describing a line to our point of intersection function. So sort of making up this pos F, which is, if you take pos B and move in the direction of point E any amount, then we're going to be describing a line. And we need that because we're going to use pos F and pos G are going to be our description of lines B to E and C to E. Okay, so we can see down here, once we've got our once we got all those values, our position G is just simply take C and then move in the direction of E any amount. Once we have those 2, we can get the point of intersection. and that'll return us pos E. Okay, and then once we got pos E, that's kind of like the hard work done, because now all we got to do is we just got to say what's the direction of beta E. Vec beta E. I've already worked that out. Okay, yeah, vec beta E is the same as. Oh no. Okay. So we've already got the direction of beta E, but now we need to find the actual vector itself to work out like the magnitude. Okay, so that's what that's working out. Vector of beta E is, take away A from B, and then we're getting the magnitude, which is simply the magnitude of that vector. The radius is the magnitude of that vector divided by 2. And finally, we need to make sure that the magnitude that this vector is hold on a sec. I'm not sure if this is necessary. I'm not sure if magnitude of beta h would ever be an invalid number. Okay, because that can't be invalid. Magnitude of any vector is not invalid. Subtracting one vector from another is never invalid. The only invalid one could be if pos E was invalid. I think it's safe for me to remove that. I'm going to comment it out, see if anything breaks. We'll see what happens. The only thing we're checking here is if it's describing a circle that's got a massive radius, then it really, depending on your implementation, you kind of just want it to say the person's not drawing a circle. So that's what I've got here. I've said if it's a massive circle, then just throw it out, return undefined pretty much. And otherwise we're just going to get pos h by taking our position B, moving in the direction of beta E, multiplied by the magnitude of beta h, which is, in other words, multiplied by the radius. That's kind of like how that works. Okay, so yeah, then we return the center, the radius, and the diameter. That's the formula. Let's have a look at how it works. Okay, so now that we're safe, we understand hopefully understand the formula. I just want to mention one more thing, and that is that these perpendicular lines, like this is, I'm calling this direction theta E and theta E. It's like may be inverted. Okay, in other words, if you're drawing a counterclockwise circle, then those lines are pointing towards the position E. Otherwise, those directions are pointing they're pointing in that direction. I'll show you what I mean. Hold on a second. Okay, because a perpendicular line is always going to be let's see, it's always going to be to the left. It's always going to be to the, yeah, if you've got a line, it's always going to be to the left of that line. Yeah, I'll show you what I mean. So if we've got a line like this, got a line like this, right, the perpendicular is that way, right? Got a line like this, the perpendicular is that way. Line like this, the perpendicular is that way. Is that right? Already bunged it up. Yeah, no, that's right. That is right. Okay, you're sort of getting the idea. What this means is if we're describing a perpendicular line to our A, B, and C, then in the case of a vector going this way, then the perpendicular will be here. Let's zoom in a bit. In the case of a vector going this way, perpendicular will be here. However, if we reverse those vectors, if we reverse those vectors, so let's say for example we've got our circle and we're going in this direction, then our perpendicular lines are going to be going in this direction, right? So they're going to be going away from the center of the circle. But that's okay because our formula for finding the intersection of two lines imagines that they go on forever. And so it's going to find that intersection anyway. I guess I just wanted to clarify that. Alrighty. So anyway, that's the math. That's the math done. Let's go ahead and have a look at what this looks like in the code. in the I guess visualization would be a word for it. Let's see, center of a circle. Okay, so what have we got here? We got our point A is the red one. I'm gonna make this bigger. Make sure I didn't break anything. Yeah, it didn't break anything. Okay. So let's see. Let's redo this point. Nearest point. Center of circle. Center of circle. Okay. So what do we got? We got this red one is point A. The green one's point B. The purple one's point C. And then the red one is our center or point H. So yeah, we've worked out how to do the math, and we can sort of just say, okay, A, B, C, and then it's sort of it's figuring it out. Now, one thing I want to note is that point A is rarely on the circle itself. It doesn't matter. You can imagine that there's a line going from B to A, and that keeps going across to here. That would be our point D, and that's where we get our from point D, and this purple one, that's where we get this far point. You can imagine the far point going like this. Okay, so that's sort of that. What's the next one? Oh yeah, I think I got another example. Oh yes, this one's simply a live example, like as in this one's sort of like tracking the position as you move your mouse around. It's attempting to find the center of the circle that you're sort of drawing. You'll notice that it ignores you. It ignores the radius if you go in a straight line. It says like too big, you know. It'll only sort of like there's sort of a with motion tracking. There's a bit of, I guess we call filtering you got to do. You got to throw out certain values. Alrighty, that's about everything. That's about everything I wanted to cover today. I guess one thing I'd like to do before I sign off is I want to update the website. So, if you guys have never seen how a website's updated, then today's your lucky day. I'll show you. Anyway, I'll show you. So I got this Pirates for Sale website, and you'll see at the moment it's got not as many examples as our local version. So what we're going to do is we're gonna first of all we've got to build this local version. Then we're going to put it on the you can imagine there's a folder on the internet somewhere, which has a subfolder called demos and a subfolder called vectors and a subfile called index.html. And so what we're going to do is we're going to push the new version onto that folder in the cloud. Alrighty, so what do I got to do? I got to open up. I'm just going to open up. I always forget my names. Okay, real original. I've got a GitHub repo called website. Website. Let's open that up. Okay, so we'll be able to publish that. So before I go ahead and jump into that, what I'm going to do is I'm just going to build this project that I'm working on. So how I can do that is where was it? Our vector 2, our vector demo. Okay, so what I got to do is I got to go into the terminal. Just got the terminal here. Let's see if I can do this so you guys can see it. Ignore all that. Ignore that. Ignore that. Okay. Okay. So let's see. Vector demo. What am I using? I've been using it's a Node application called Webpack. What that means is as you're writing a Node application to be deployed on the web, you're able to you're able to use any node what do you call them, packages as you want, and what it'll do is it'll convert it into a something that any web browser can understand. Okay, so yeah, literally packs up your. It's essentially the same as well, it's not really the same. You know how in a C# project or something you build it, you'd compile it. It's not quite the same as compiling because it's still JavaScript. It's just that a lot of things are written in Node, which is kind of like a JavaScript with where you can do more stuff with it, and it sort of does some conversions. Anyway, what we've got to do is we've got a Webpack build, and I've got a little. If we just run npx webpack, it'll do that for us. And what that means is this little folder called dist is ready to be served on any website. So I'm going to go ahead and copy that. And then if I go into, where is it? Oh, go into my website. And then I've got to get this right because I got the public. One of them gets destroyed on build. Publish, remove dist. Okay, so I've got to put it in the public folder. Got to put in demos, vectors. Okay, so I'm going to delete vectors because that's the old version. I'm going to paste our new one, rename it to vectors. Okay, and this is it. This is just a little script that I wrote. What it does is it moves a lot of the stuff that while you're sort of working on it, it's in the public folder, and it just moves it to the distribution folder. And then in Google Cloud, because the website is hosted on Google Cloud, it makes sure that in our Google Cloud CLI, it's in our what do you call it? Terminal CLI. In the application that runs in its command line interface, in the application that runs in the command line. So if I said like gsutil, I think it's called, it might do something. Is it going to do something? No, it's not. It's not going to do something. Okay, I thought that would work. Oh no, it does work. Oh, it's just taking ages. Okay, so gsutil is this is all the commands you can you do to, I don't know, edit your Google Cloud projects. So what this is going to say is in our Google Cloud utility, it's going to set the project that we're working on to the Pirates for Sale project, and then it's going to confirm that by printing it out, and then it's going to say I'm going to delete everything in your Pirates for Sale project, and I'm going to replace it with everything in my distribution project. Okay, so that's this one. gsutil copy recursively everything in the current working directory, which is the dist directory, and then copy everything to our folder, which is piratesforsale.com. Okay, and then it just cd's back. Okay, so let's give that a go. See how that goes. Yep, it's saying current project, Pirates for Sale. Copying everything across. And it says that it's done. So, if everything went according to plan, if I go to the Pirates for Sale, I have no idea if this will work. Pirates for Sale website and hit refresh. Hey! And we've got all our examples. That's really cool. So we've got our point of intersection, we've got our slope intercept, angle between. All the stuff we've been working on, we're able to sort of we're able to see. All right. Let's see. What's the coolest one? I really like the center of the circle one. Wait a minute. Oh yeah, no, I like this one. I like this one because you can make really weird shapes with it. This is something, yeah, it'd be really cool to do more shapes. All right. Well, thanks for tuning in. Yeah, it's been good. It's been good. This will be the end of the math of motion for now. I'd like to. There's some other stuff I'd like to do about 3D. Not yet though. Stuff about you know, if something's moving through space, how do you find what plane it's on, plane detection, that sort of stuff. Work on that later maybe. I might do some more practical examples in the future. Like I don't know. I'll have a think about it and then do that. See you guys.